Okay, so here's an example for class 8. This is video 2, and this is a problem out of Munson, which is another fluids book. I'm trying to find my Munson. That would be Fundamentals of Fluid Mechanics, Munson Young. I'm not going to pronounce the next name. So air flows steadily along a streamline from point 1 to point 2 with negligible viscous effects. The following conditions are measured. At point 1, the vertical position is 2 meters and the pressure is 0 kPa. We can assume that means gauge instead of absolute zero, so that's atmospheric pressure. At point 2, it rises to 10 meters. So it starts at 2 meters and rises to 10 meters. And the pressure is 20 newtons per meter squared, which is also a Pascal. And the velocity is 0, so we could call that a stagnation point perhaps. We want to determine the velocity at point 1. So right here, here's our little here's what Munson and Young look like right there. This is from the, I think it's from the 6th edition. It might be somewhere 7th or 8th edition is when I started with these. So one of the first things I would do is I would get the density of the air. I would look at material properties is often the first thing I would do. And for us, we're going to use the equation sheet that I'm providing for exams. And see, so we go to, these are SI units. And so in SI, we see that the density of air at standard conditions is going to be 1.23 kilograms per meter cubed, right there, if you're looking. It's good to get used to these equation sheet. So I've written that down. I like to draw like a little figure to try to tell a story. I think it's an effective way to try to solve a problem. So look, we can see right there, this is along a streamline, and we have two different heights. We could say that this is going to be Z1 is going to be equal to 2 meters, whereas Z2 is equal to 10 meters. And see, the pressure here at this is going to be 0 kPa. And up here, we're going to have P2. It's going to be 20 newtons per meter squared. And we also know up here at the top that the velocity is equal to 0. And it doesn't matter what the units are because it's 0. So we could write out our Bernoulli. And I think of this as Bernoulli 1, by the way. We'll talk about that in the next class. There's, I think, like 2 main forms. There's a couple of different variations above that, but there's just, I think of them as 2 different ways that are most commonly written. So here's Bernoulli on the left-hand side, which represents 1. Then on the right-hand side, representing 2. And it's worth noting every time we go through this, the 4 different conditions that you need to have in order to use Bernoulli. As a minimum, there might be some others we could also include in there, but to say that first off, it's got to be steady, it's got to be along a streamline, it's got to be incompressible. So what we're doing is we're assuming this density doesn't change between these 2 points right there. It's an important thing. Let me see. It's along a streamline. Oh, it's inviscid, right? So, and air doesn't have a whole lot of viscosity compared. Gases don't generally have much viscosity compared to, relatively speaking, to liquids. So, it's a pretty good guess. All right. So here we're going to start with 0. It's exciting, and then have 1/2, and then the density. And I want to make sure that my units are going to balance. I don't have to do this every single time, but it behooves you, it's a great word, behooves, to try this out right here. Okay, so this is what we're looking for. Actually, we're looking, I should probably put find somewhere in here. It's always a good idea. Find V1, all right? That's V1 squared is right here. And we can go with the specific here. A lot of times it's not going to matter with air. We might even want to quantify this. So instead of using the specific weight here, I'm going to use that's the same thing as saying rho g, right? So we'll go 1.23 times 9.81 times 2. And I wasn't consistent. I didn't put my units inside there like I said I was. We'll do that off to the side then. P2 is going to be 20 newtons per meter squared. And now here's where, well, this is actually going to be 0, so we don't actually even have to write this, but we'll put it in there anyway as sort of a space holder, because that was, this was supposed to be 2. Whoops, I'm sorry about that. The velocity 2 was equal to 0. I was talking, not thinking. And then plus, we'll have, once again, 1.23, and I will say that this is going to be kilograms per meter cubed times 9.81. I ran out of space, and I ran out of unit space. Darn. I guess that's what, I don't know what the margins are for if I'm going to keep writing on top of them, right? And then this last one is going to be 10 meters. So let's take a look at the units here before we go any further, or let's even, yeah, let's quantify this part right here. Let's see what what these differences are in terms of numbers. So I'm going to quantify it, then I'm also going to look at the units. So 1.23, 9.81, and then 2. Right, so that's actually, relatively speaking, that's actually a pretty good difference right here, because that's 20. So compare this, and we end up with 24.13, right? Most often, though, we won't be using the change in elevation when it comes to a gas, but here's an example where we did. So this one we can expect, we could actually, if we want to be really lazy, we could divide this by 2 and multiply by 10, but let's just not be lazy and go ahead and put it into the calculator. And then, so we end up with 120. Is that right? That seems like a lot. I'm looking at the other things right here. Yeah, no, I think we're okay. Yeah, it's 120.7, right? Looking at the units, let me see, just write a little thing over to the side. We have a kilogram per meter cubed times meter per second squared times meter. That's a cube. So if you take a look at this guy right there, that always turns into a Newton, right? A kilogram meter per second squared, boom, turns into a Newton, because you could always think of F equals ma as a concept, but also a unit balance, so that a Newton equals a kilogram meter per second squared. So look for a kilogram meter per second squared, and just that automatically turns into a Newton. You can have one of these masses, one of these meters, knocks out one of the 3 here. So we have a Newton per meter squared. So we're confirmed that we have homogeneous, dimensionally correct, right? So anyway, we work through what the velocity at 1 must be, and that's really going to be the square root of that 120.7 minus, plus 20, excuse me, I should have added that 20, and minus our 24.13, and we should, we're going to divide by 1/2, I was going to put the 2 up at the top, and divide by 1.23, right? And what we should get is a velocity of 13.77 meters per second. Not a really complicated problem, just really kind of plugging and chugging, going through the thing, but we want to make sure we check off some things, make sure that we can use Bernoulli because of it's obeying the 4 rules, and it's also a good idea to check the dimensions onto this. And I think a really important step in many different engineering problems is to see what the in-between numbers are, so we can kind of see the relative value of these, right? Or this one versus that one versus that one. So we can really see what's driving it. It also has a side benefit of helping you, if you end up like having to take a square root of a negative number, you've probably made a mistake somewhere. So it can help you kind of like diagnose and go back and say, I punched in my calculator wrong here or wrong there. I know that some of you use calculators, probably most of you, TI-89 or whatever, where you make a long string of stuff, and you can just go backwards and edit your equations into there. But it's a good idea to me, I think, to write the in-between numbers instead of just plugging it all in and then hitting equals, because you can diagnose when you make mistakes. So that's it for the first example. I'll make another video.